SwayamPrabha. Digital India. Educated India.
Welcome to the class of Intelligent Product Design. We are in the case study space, and in the first case study I have talked about a rotary actuator and an intelligent stick. Now today we will discuss a much more complicated system. This intelligent system is designed in a way that it can go inside a pipeline and can find out different types of damages in a pipeline, so that we can predict the health of a pipeline. So, this case study is again based on a live project which has been carried out by the SMS's laboratory at IIT Kanpur on design and development of adaptive and intelligent. You remember that for intelligence you need to have something in which it can work in an uncertain environment. So, this system is adaptive and intelligent, and this is a pipe health monitoring robot which can be used for fuel transportation systems such as gas pipelines. Now, pipe health monitoring robot, or PHMR in abbreviation, is developed in IIT Kanpur for a very long time, and this is used for inline inspection of buried pipelines in order to monitor its health and assess the risks associated with its operation. So, basically the robot travels inside the pipe when the flow is happening. Okay? So, it is a energy harvesting system, sustainable. You do not have to put additional energy. There is already flow, there is already gas pressure inside, and that pressure is propelling, giving the force to the robot, so that the robot is moving inside a pipeline. As it is moving, it is actually collecting data from the different sensors that are triggered towards different types of stimulants in order to know about the condition of the pipeline. The data are then retrieved and interpreted both online as well as offline from the robot, and then interpreted in terms of damages. So, the data on external and internal defects both are reported accurately with respect to different types of defect sizing and location. Now, this is a project which had been sponsored jointly by the Gas Authority of India Limited and also by the Ministry of Education through Uchchatar Avishkar Yojana. Now, what were the objectives of this product design? Well, PHMR was aimed at developing a pipe health monitoring system which will be comprising of a range of smart sensors. Okay? Now, the outcome should be such that we should be able to design and develop an effective and economic pipeline health monitoring system based on smart sensors integrated in a crawler robot and an efficient data communication. So, these sensors will include development of motion control units. The entire system will include the development of motion control units in robots using different types of techniques. I will explain it later on, like bypass vanes or morphing, and then location tracking of the robot with the help of low frequency transmission and receiving system, and then onboard damage assessment and reporting software. Then we will demonstrate the use of the developed prototype. User interface must be developed and the techno information package is to be developed. So, as you can see that this is the entire PHMR, and the last one is not actually a wheel, but this is called odometer. This actually senses the how much of distance it is traveling. Okay? I will soon tell you about different parts of this PHMR. Okay? Now, such products cannot be developed all in one phase. So, in 3 phases, 3 different types of robots were first developed. PHMR 1, which was the initial prototype, and it has sensors like a smart sensor called PVDF. It is a polyvinylidene fluoride type of a sensor. This is a piezoelectric sensor. So, what does the piezoelectric sensor does? It actually gets data, because if there is a dynamic strain change, or if there is a deformation of a finger like appendix. So, there will be some finger like appendix which I will show you later on, and that if it gets deformed, it actually collects the deformation data and interprets it in terms of the damages in the pipe. It also has some pointed magnetic flux sensors, okay, MFL sensors, and also optical sensors. It also has turbine for the power generation. Now, PHMR1 of course was made of a cheaper model because it is a rapid prototype. So, many times in order to develop intelligent products, I always say develop the fast functional prototype, which is just the demonstration of the concept. So, in this case you do not have to think of the actual material. So, in this case we have this kind of parts also in it, which is made of not a very highly rugged material. But in the second case, it is based on a fully aluminum body, and later on we have used actually a even higher grade rocket grade aluminum alloy. So, gradually we have used more and more better and robust material, and then there is PVDF just like last time being the PHMR2, but also this time instead of a single MFL we have a distributed MFL sensor, constant speed, and however it was a fixed model, it could not negotiate the pipe bends. Finally, we came to the third model where we can do the speed control, we can negotiate the pipe bends by designing these joints suitably, and then we have the PVDA, distributed MFL, and optical sensors, three different types of sensors in it. So, the final one that has been developed is PHMR2C. So, PHMR2C is the final robot, final one in which you can harvest the energy, the fluid flow energy, and the three modules that are there are actually the front module that you can see here. This is the tip one front module, then you have the middle module, and then you have the rear module here. Okay. So, there are three modules there in the system, and the LED LDR sensors are used in the rear module, that is in terms of the optical sensing, and then you also have the touch probe sensors which I earlier told you. Magnetic flux sensors is also present in order to calibrate the system. So, this is the specification of the whole system. As you can see, the front module is 150 millimeter, it is a smaller one, and then its weight is about 1.7 kg, made of space grade aluminum alloy that I told you earlier. The middle module is longest, it is 373 millimeter, its weight is also more, 4 kg, and then the rear module is 205 millimeter, slightly smaller, but however longer than the front module. The weight is about 2.3 kg, this is lighter comparatively, and it is also of the same material. Now, the wheels are actually of nylon, and the wheel diameter is about 40 millimeter, because this is designed for a 8-inch diameter of a pipeline. The battery that is used for minimum for just to empower the sensors, not for any actuation, and the battery is of lithium polymer battery, and the microcontroller that we have used here is Arduino Nano. So, in order to develop such systems, you also have to develop the atmosphere. People will not allow you to just like that use it in an existing system. So, you have to develop a compressed air test bed system. So, this air test bed is something which is very unique in our country. So, this is this pipeline system in which instead of the natural gas, the compressed air has been used, okay, which from the density wise smaller but lesser, but still it gives a very good estimate of the system. Now, this complex system is based on a 30 meter by 7 meter kind of test bed system. So, it has two sides which can go vertically down up to 21 degree. So, you can have this type of a situation, simulating the typical bend in the pipeline vertically as well as horizontal bends at the two ends. Okay. So, we have a 90 degree horizontal bend, and we have about closer to 20 degree vertical bend in the system. So, this kind of simulates the actual working environment of the pipeline network. Now, in this network we have a launching and a receiving station. So that you first put this robot in a particular area like this zone, and then you actually divert the air pressure, okay, and then a knife edge valve opens up, then the air pressure thrusts the robotic system to go to the main pipeline system. So, that is the way you can actually have a launching system. The receiving part, we have a receiving section in which you can actually keep some air vented out, so that you can reduce the air pressure, and as a result of that the robot speed actually comes down. Now, as I told you that there is range of sensors in it, okay, so total of 12 working sensors. There are 4 magnetic flux line sensors. So, these sensors are based on giant magnetoresistance. Okay. What is GMR? The GMR sensors are such that in the presence of a magnetic flux change, the resistance of the system changes. So, that if you have an electrical circuit corresponding to it, the change of resistance will show that there is a leakage that has happened in the system. Then you have the PZT. PZT is lead zirconate titanate. So, this is a PZT based touch probe. Okay. So, this smart material actually gives you a very high bandwidth sensing. Okay. Like shape memory alloy we have seen last time, they are actually low bandwidth smart material, but these PZTs are high bandwidth smart material. So, they can be used as sensor very well, not so good as actuator. And then you have 4 such touch probes. So, the touch probes are basically touching the pipe surface, and there is a, if there is a crack or some development on the pipe surface, corrosion or something, then that will create a strain on the probe. Like if you imagine this is the probe and then this is the tip of it, then the change in the surface will create a signal, and that signal is captured by the PZT probe, and that is what we record. Also, we have optoelectronic sensors, which is based on LED LDR principle, but more sophisticated than that. Essentially, you have some light emitting diodes at different frequency range. Inside the pipe, generally the lighting condition is very dark. So, you have infrared range of LEDs, and then the LED sends the light, and then some of the light gets reflected back. That reflected light is sensed by the LDR sensor, and then from that we can actually analyze the absorption spectra and comment on the possibility of damages or corrosions in the system. There is also a rotary encoder that I have shown you in the beginning attached to the robot to detect its position. Now, the optimal estimation of sensor is very important. Okay? So, that means what will be the array size, how far away it will be from the pipe surface, the lift off distance we call it, okay, what will be the separation distance between the magnets. You have to do both a virtual model like through digital simulation, as well as you have to carry out experiments in order to do this. And then similarly for the touch probe sensor, what will be the optimal probe size, what will be the placement of the piezoelectric sensor, flexural rigidity of the beam, how much of deformation it can have, it should not be too soft, it should not be too stiff. Then the control of the spiral motion, all these things you need to do it through both modeling as well as through trial and error. And similarly for the optoelectronic sensor. So, you can see that the magnetic flux leakage sensor, the basic principle of the MFL sensor, that you can see that there is a magnetic flux getting generated, and suppose if there is a crack, then some of these lines will not come out and the sensor is going to pick it up. So, Hall sensors, GMR sensor, this is what we typically use to pick up the break in magnetic flux. And this is how the touch probe sensor looks like. So, it is like a partly trapezoid, partly triangular section, and such that if this part is actually subjected to some kind of a pipe surface corrosion, then there will be a vibration, and that vibration is picked up by the piezoelectric crystal. So, that is what is the uniqueness of this touch probe sensor. And then there is this optoelectronic sensor, the optoelectric pairs is going to have the LED and LDR. So, you have a transmitter from one side, that is through the LED, and then you have this LDR in another, and basically they are in an array formation, and each one pair is basically absorbing the light that is coming from the nearest LED source, and from that it is trying to understand that what is the damage in a system. Now, so many sensors needs to be interfaced. Okay. So, in order to do that, we have employed an Arduino microcontroller. So, Arduino basically, first of all triggers that on off situation when the sensors will be active, and secondly what will be the kind of level where you can call that the sensing data has crossed a threshold, and then it will actually instruct each of the sensors to send the data, and it will record the data, and then once it is coming out, the Arduino will close. Okay. So, each one of the sensors. So, this kind of a thing is all controlled by the Arduino for the sensors, and then the data goes to a serial USB port, micro SD card for data storage, okay, and some of the data also directly sent for real time communication. Okay. So, that at least you know where you are. The GMR sensor, which is based on giant magnetoresistance, the issues there will be the cost, the sensitivity, the field detection capability, temperature stability, offset, dissipated power, power consumption, so many important parameters that you need to basically calibrate in order to come up with a good GMR design. So, that is while selecting the magnetic sensor you have to keep in mind. And here you can see that the GMR sensor, which is based on these BAB type of a system, that is a magnetic layer sandwiched between copper conductive non-magnetic interlayer, and then this entire system shows sensitivity towards this multi-layer system, which is sometimes based on iron, chromium, iron layers. They show sensitivity in terms of changing in the electrical resistance due to the change in the magnetic field or magnetic flux surrounding the sensor. So, why do we go for GMR sensor? Why not the Hall sensor? Well, that is because the GMR sensors have much higher sensitivity. Okay? And in a pipeline system, you need to know that even if there is a micro crack or a hairline crack, that can create a large failure, creating fatal situations. These gases are very highly inflammable. So, we need to know in the beginning itself if there is such hair cracks happening. So, we need to have a highly sensitive sensor network, and that is why the GMR sensor has been used. Okay? That is one of the important considerations of choosing such a system, that they are sensitive to the external magnetic field. The optoelectronic sensor implementation part, I told you that it is based on LED and LDRs. Now, LDRs have lower sensitivity than the photodiodes and phototransistors. So, photodiode and phototransistors are semiconductor devices which use light to control the flow of electrons and holes across the PN junctions, and the property of photoresistors is that its time latency between changes in illumination and change in resistance happens because of the presence of change in the photoluminescence. Now, 10 micromillisecond for the resistance to drop completely when light is applied after total darkness, and while it can take up to 1 second for the resistance to rise back. So, that is the type of time you need to give to this system in order to respond. So, this is slower that way the LDRs. Okay. So, LED LDRs also is not suitable for high lift off and high linear velocity, because of which we go for photodiode and phototransistors. Now, the optical sensor implementation is in terms of phototransistors, that you can see it here, that how small the system is, 7 by 7 by 6 millimeter. So, it is quite small, and typically the output current is about 1 milliampere. The emitter wavelength is 950 nanometer, and so its effectivity is from 0.6 centimeter to 2.3 centimeter range. So, that is about the phototransistor type optical sensor. And then we come to the pressure sensor and buzzer. So, this is needed in terms of knowing actually how much of pressure is there, because we design the system for certain amount of pressure, but inside the pressure may actually vary, and if there is a fluctuation of pressure, then the drag force will change and the speed will change. So, this is what the pressure sensor does, and the buzzer indicator is there inside, that also works in terms of if there is a large change or if the whole thing gets stuck, it is not moving, then the buzzer indicator works in the system. I told you that we also used a rotary encoder. Rotary encoders are used for distance measurement, and this one is an optical rotary encoder, which means again it is based on some kind of a LED LDR principle, but it can very precisely measure that how much of wheel turns rotations have taken place. So, assuming there is no slip of the wheels, you should be able to figure out that how much of distance you have traveled, and because you have the map of the system available with you all the time, so you can also say that currently the robot is at which location. So, this is the distance and velocity measurement from this optical rotary encoder that we have used. And once again, Arduino Nano keeps track of the pulses that it generates and how many numbers of pulse has been crossed. So, from that it predicts about the displacement and the velocity. Now, I come to one of the most intricate part, that the speed control. You know why speed control is important for such a system is because you are essentially scanning. Now, as you are scanning the pipe, if the robot moves different places at different speed, then the scanning will be faulty. You won't be able to know exactly where the error is. So, in order to keep the speed in a particular narrow range, you must have some kind of a autonomous governor system. You cannot use again large power. So, power supply is limited, as I told you, only for the sensors. So, the system should be physically intelligent autonomously. In order to do that, two things you need to see, that there has to be a motion transmission system and there has to be a hydraulic braking system. So, such that as you can see in this particular flow diagram, that how the passive feedback braking mechanism works. Okay. So, you can start from the rotary motion of the wheel, that is here, okay, and then as the wheel is moving, the gear mechanism actually gives a command to the piston. The piston actuates itself. So, if the wheels are moving very fast, then the gear mechanism tells the piston it is time for you to actually apply the hydraulic force. The piston drives the fluid, fluid actuates the brake, brake actually slows down, the wheel speed gets regulated. Now, if the wheel speed comes down very small, then once again the governor works and the rotational motion is to be increased. So, that command is sent to the system that hydraulic pressure is decreased until and unless you reach that particular level for which it should run the system. So, the motion transmission sub-assembly is shown here, that this basically transforms the wheels rotation through the gears and through a certain gear ratio, and then this rotational motion is to be transmitted to the motion of the central shaft, and that central shaft is finally going to work in terms of pushing the hydraulic pressure in terms of reducing the speed of the system. So, this is the hydraulic braking sub-assembly. So, as you can see here, that as that central shaft is rotating, the piston is pushed outward, and the fluid with the same pressure flows to the central shaft, and that gives the braking mechanism. So, this is basically a kind of an intricate governor system that has been developed for it. Now, this is the complete CAD assembly of this very intricate speed control system. I also told you that there are certain deacceleration mechanisms other than the governor, and that is in terms of using the bypass valves. So, as the speed increases, these valves, these actually covers moves, and as they move, they open up more bypass area, so that some amount of air gets bypassed. So, they do not deflect, and that is how also you can control the pressure. Okay. So, you can see that how the mechanism works and how you can get more bypass in the system. So, this is like a test run of the system first before you install such a system. So, you can see we are rotating it artificially. So, we are assuming as if the wheel is rotating and that is transferring the movement through the bevel gears, and that is going to actuate these particular valves, so that you can get the basic action of braking. And this is the back plate, where as it will move you will be able to see that the bypass actually starts to get opens up if it moves beyond a particular level. These fellows are going to open up and they are going to create a bypass, so that the flow can be bypassed through such a system. Now, then you need to have all the data acquisition, so related to each one of them. So, there has to be a test data acquisition system. In this case, again Arduino is used in terms of this data acquisition system for all the types of sensors, MFL sensor, optoelectronic sensor and PZT sensor. Okay. So, this, in order to do it, first we have to actually check in an artificially cut half pipeline how each one of the sensors work, and how you can sense the data. You also need a good graphical user interface. Okay. First of all, you are getting the wireless data from the robot, that from the microcontroller has to come to, through the ESP module, has to come to systems like a mobile or a laptop, and then from there it needs to be displayed in a certain way. Okay. So, this entire protocol you have to develop for the wireless data collection of the system, and then display the result with the help of a graphics user interface. So, you can see the entire system here, that is the PCB and the microcontroller, the sensor interfacing works, and then the microcontroller sends the data, and then from the wireless communication it comes to another microcontroller and to the system with the GUI, and then that GUI now displays the data for the people. So, to actually analyze it. So, you can see here that how the data are coming, this optical reflector data, MFL data, optical encoder data. Now, all the time all the sensors may not be actually able to capture the cracks, and that is why you need multiple sensors, so that you can sort of fuse all the information and get a picture from this entire system. So, this online window has actually 9 such plots. You get 4 MFL sensor data, you get 4 optical data, and then you are going to get the PZT data. So, you get all of them together and then you can fuse it. So, you can see how this data would look like in an offline mode, and each one of these peaks are surely going to say something that is inside the pipe, be it in terms of the bending, be it in terms of the joints of the pipe, or be it in terms of the cracks or corrosions. Of course, you will need SVM or type of such AI in order to machine intelligence, in order to learn which one is for what. Okay. So, similar thing we receive from the optical encoder sensor, and then you create, this is what is the creation of the environment in a 3D system, that is the GUI of the 3D plots of the optical reflective sensor, okay, showing the data. So, similarly you can do it for all the different types of sensors. So, this is the development of an intelligent pipe health monitoring robot that we have created in terms of monitoring the pipelines. Keep in mind that our country has, only in terms of gas pipelines, we have something like 15,000 kilometer of gas pipelines. So, their sensing is extremely critical, because through that you will be able to actually talk about the life of the pipelines. So, our PHMR sensors, the PHMR robot along with the sensors can actually predict this life. Thank you.